Anyone, if you have any questions, just let me know. I am waiting for 1-2 more minutes so that everyone can join.
Sir, will you upload these PDFs on Moodle?
I have uploaded on Microsoft Team. Have you seen that?
No, sir, I have not checked there.
Yeah, so please check it. Already it has been, all the lectures has been uploaded. So
Oh,
at the end of week, I upload, slides for all the lectures in that week.
okay, sir.
Okay. If anyone has gone and downloaded it,
Yes, sir.
okay,
Yes,
Purvi.
sir.
Okay, great. So please do it. And also, if you want to download any particular lecture, you can always download the video also from the Microsoft team. Okay. And if there is any problem, just let me know. I can send through email, at least lecture, not video lecture, but lecture I can certainly send you. Okay, so let me start. I discussed in the last lecture about consecutive reactions, and these reactions are very important because most of the mechanism involves uh, consecutive reaction. Okay, so consecutive reaction is one of the uh, you know elementary reactions, and we discussed few things which is very important when you are dealing with consecutive reaction. One is the slow step is the rate determining step, and if intermediate concentration is small, then we can apply steady state approximation. A steady state approximation is very important concept in chemical kinetics since it gives us a tool so that we don't have to solve differential equation. And solving differential equation for complicated reactions will be very difficult. But I will discuss later how to even uh, solve differential equation if you are dealing with a complex reaction. Okay, so we already showed just through solving differential equation and by using a steady state approximation that equation is going to be same, right? So this was the equation for I, and then we calculated the concentration of I given by this equation, and then amount of product can be calculated since we know what will be the A at a given time and I at a given time, am I right? And then we discussed two different cases, and from that uh, I told you that product concentration will depend on the rate constant of the slow step, and that gives us what this idea that slow step is always rate determining step because rate constant of this step will determine the amount of product. Okay. uh, then we discussed about this concept of steady state approximation. Only thing you need to keep in mind is the concentration of I should be very small in comparison to concentration of product and reactant. Once that is there, then we can apply a steady state approximation. And then I showed you that if I apply a steady state approximation, uh, this is the amount of product which is similar to which is same as, not only similar, it is same as what we got through solving differential equation. So you see in one step you got the value of I. You don't need to solve differential equation. And but steady state approximation is only applicable when this concentration of I is small, which generally for this simple reaction, you have like first slow, then fast. If slow step is followed by fast, then I can apply steady state approximation, not the other way around. That if suppose first step is fast and the second step is slow, then I cannot apply, because in that case concentration of I will not be negligible in comparison to A and P. Okay, so that is whole concept. Luckily for us, since most of the reactions, particularly organic reactions, uh, involves intermediate carbocation, carbon ion, or free radical as intermediates. They are unstable and they go very fast to product, and hence we can apply steady state approximation to uh, in most of the cases. Okay, we again discuss the case where uh, we cannot apply steady state approximation. All right. Here you can see that concentration at one point, concentration of I is quite greater than A. In fact, if you look at the maximum concentration, you can see that almost it is equal to concentration of maximum concentration of A and P. Hence, in this case, we cannot apply a steady state approximation. Okay, then you have to solve differential equation. And I told that we can get what is the time at which we can obtain maximum concentration of intermediate in this case, and that will be given by this equation. And as you know, in any other cases, how maxima is calculated, you have to do di by dt is equal to 0, and then you can get t. And with t, you can also get I max, how much amount, maximum amount of intermediate is required. And this is needed if you want to synthesize the intermediate. Sometime intermediates is also a product which you want to get. Okay, just by kinetics, simple kinetics, you will be able to distinguish, one step or two step reaction if K1 is quite greater than K2. It means first step is fast, second step is slow. Then you will be able to distinguish between these two cases, but that is not possible when the second step is fast, first step is slow. So in most of the cases, this is the case that your slow step is followed by fast step. But so it is difficult to distinguish just based on kinetics, at least at just looking at the rate constant, that whether it is a single step or more than one step reaction. But I will discuss from the rate law how you can do that. Okay. Uh, this is we discussed about how to calculate rate of reaction in the last lecture. Now I will start the another elementary reaction, which is your what is known as parallel reaction. Okay, this is parallel reaction. So let's insert one slide. I can derive that so that okay. So let us see A, which is reactant, going to B and going to C. So B and C are two products, K1 and this is K2. Okay, so what I will write, dA by dt is equal to K1 into So it goes by this K1 into A plus K2 into A, or you can write K1 plus K2 into A. And we know what is the solution for that. So A is equal to A naught exponential minus K1 plus K2 into T. Okay. So this is the way you can calculate the amount of A. Once you know amount of A, we can calculate the amount of B. So this is your amount of A and this is your amount of B. So just by you see here how we can get it. So A is equal to, we know that let us see, B is equal to K1 by, so you see here this is A is equal to A naught exponential minus K1 plus K2. Similarly, you can write dV by dt. dV by dt is K1 into A. All right. So dV by dt, how we can write? K1 into A. We already know what is K1 into A. The K1 A naught exponential minus K1 plus K2T. Okay. And similarly, I can write dC by dt is equal to K2 into A. And this is equal to K1 into K2 into A naught exponential minus, sorry, minus should be out, K1 plus K2 into T. And we know that what is the relationship between dV by dt and dC by dt? dV by dt versus dC by dt. dC by dt is equal to K1 by, you see, if you divide this, A cancels out. So you have K1 by K2. Am I right? And from that, you can see here, you see what you will get is, so this is product. So B is equal to K1 A naught by K1 plus K2, 1 minus E minus exponential K1 plus K2 into T. Okay. So you can also write A by B is equal to, A by B is equal to your K1 by, B by C is equal to, B by C is equal to, B by C is equal to your K1 by K1 plus, sorry, K2, K1 by K2. And similarly, B by A can be written as, what can you tell me what it can be written as? Yes, anyone? B by A?
K1.
Yeah. So K1 by
K1 upon K1 plus K2.
dV by dt. Let's write dV by dt versus dA by dt. dA by dt is, at least you can write K1 by K1 plus K2. So by using this, you can solve these two things. Once you know that, there is another important concept, what is known as thermodynamic versus kinetic control. So whenever you are dealing with parallel reaction, you need to, have you heard about thermodynamic versus kinetic control?
Yes, sir.
ऑर्गेनिक केमिस्ट्री में कभी पढ़ा था? Okay, so if you remember that one product is, yes,
We already learned it in organic chemistry.
organic chemistry, yes. So thermodynamic versus kinetic control comes from there. You see, so you can see that if K2 is greater than K1, K is rate constant here, and this K is your equilibrium constant. Okay, and we are dealing with A going to B and A going to C. Okay, so if K2 is greater than, this is for first and this is for second, am I right? If K2 is greater than K1, it means the second reaction is fast, am I right? A to C is fast, A to B is slow. And that is because of activation energy, am I right? So you can see in this case, activation energy is higher and here activation energy is smaller. So that's why K2 is greater than K1. And the second condition is this big K2 is greater than K1. It means this C is what? Most stable product. Okay, C is most stable product, and so you can see here. C is the most stable product. So, here, whether reaction goes through thermodynamic or kinetic, what you will get? B or C? Can you tell me? Which one will be obtained in higher amount?
So in kinetic control, C will be obtained.
And
That is
thermodynamic,
B.
is this true? Why B?
So B requires a higher activation energy. So
But
in
that is
thermodynamic control,
kinetics. You see, just don't get confused by kinetics always goes by activation energy and thermodynamic goes by stability.
Stability of product.
Yes, which is more stable, B or C?
C.
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 And so this is thermodynamic product. Kinetics, which activation energy is smaller? A to C or A to B?
C.
A to
to
C.
C.
This is both thermodynamic and kinetic. If you go by thermodynamic control, you will get C. If you go by kinetics also, you will get C. Now take this case. In this case, K2 is less than K1, and but equilibrium constant for second is greater than equilibrium constant for one. Now tell me which is the kinetic control product here?
B.
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 Okay, kinetic control. And what about thermodynamic?
C.
C.
Yeah, so this is TC, thermodynamic control product. Okay. Now go to the third case. Now here K2 is greater than K1. It means this activation energy is smaller. And this equilibrium constant for second is less than equilibrium constant for one. Now tell me which is thermodynamic product in this case?
B.
So this is thermodynamic control, and this is C will be
Kinetic.
kinetic. Yeah, B ही होगा kinetic. Tell me.
C
is
kinetic.
C is the kinetic control. Okay.
Will be kinetic and B will be thermodynamic.
And now the last case. Am I right? K2 is less than K1 and equilibrium constant per second is less than K1. In this case, which is kinetic control, which is thermodynamic?
Sir, both is
B is both kinetic Both. and
Is
thermodynamic.
okay, kinetic control and thermodynamic control. Okay, so this is about parallel reaction. Parallel reaction, both compound can form depending on rate constant and equilibrium constant. So these two are important, which you must have studied in your organic chemistry case, because in one case, you will get C, in another case you will get B. And how do we get thermodynamic control product or kinetic control? Kinetic control कब मिलता है, कैसे मिलता है?
सर जिसका एक्टिवेशन एनर्जी लो हो वो हमें जल्दी मिल जाएगा, तो स्पीडली मिल जाता है, तो काइनेटिक प्रोडक्ट होता है.
So it depends on time, right?
Yes.
There are few ways in which we can, if we want to get thermodynamic, generally we get it, but kinetic control product can also be obtained. Okay, so that is about parallel reaction. I will go to some more complex parallel reactions. So it is shown here, A going to B. Okay, so dV by dt is K1 into A, and A going to C. So this is parallel. A is going to B. You can also write like this. It doesn't matter. And A going to C. Okay, with the K2. But this is first order and this is second order. Then what you will do? Okay. For if both are first order, we can solve differential equation. In this case, also we can solve differential equation, and what we will get is this one, this equation. And if K2 A naught is quite less than K1, then A will be A naught exponential minus K1t. So this will behave as a first order. But if K2 A naught is quite greater than K1, then it will behave like a second order. Okay. So please keep this thing in mind. You can solve it. This is a differential equation which needs to be solved. When you solve it, you will get this. Now let's go to reversible reaction. The third kind of elementary reaction is what is known as reversible reaction. Okay, so in reversible reaction A is going to be through K1, K minus 1. This is reversible process. Rate constant for forward reaction is K1. Rate constant for backward is K minus 1. Sometimes we also write Kf and Kb. Okay, so sometime I may have mentioned, so please just keep in mind when I am talking about Kf, I mean K1, and when I am talking about Kb, then I mean K minus 1. And we know that K equilibrium will be B equilibrium by A equilibrium. So if it is first order, both are first order. So forward is first order with respect to A, backward is first order with respect to B. Then what we can write, minus dA by dt is K1A. Okay, so you see in this K, A is consumed in forward reaction, but A is formed in backward reaction. So if you are looking at consumption of A with respect to T, this will be positive sign and this will be negative sign. So K1A minus K minus 1D. Okay, then B will be given by B naught plus A naught minus A. This is simply conservation of mass. Or if you take B is equal to 0, then I can simply write A naught is equal to A plus B. If there is no B initial. Or otherwise I will write A naught plus B naught is equal to A plus B. Am I right? A plus B. And that's what from this I can get B. B is equal to this. So idea is that now I can replace B and we have this quantity. It is solved. This is a constant. This is a constant. And A can be brought together. And when you do that, and we know that at equilibrium, your dA by dt will be 0. So A equilibrium can be calculated. So what we are trying to do is we are also removing the initial concentration and trying to express this in terms of A and A equilibrium. Okay, at equilibrium concentration measurement is quite easy because that time this is not changed. So A minus A equilibrium, dA minus, so what is done is we know that dA by dt minus dA by dt is equal to, if you remember, this is minus dA by dt is equal to K1 A minus K minus 1 B. That's what we got, if you remember here. K1A minus K minus 1B. And then we can write, we know that A naught plus B naught is equal to A plus B. Yep. Mute yourself. Minus A. So if I put it here, minus dA by dt. So what I will write is K1 A minus K minus 1 A naught plus B naught minus A. Am I right? Minus dA by dt is 0. Okay. So what we can write? By dt, this I will be able to write if I put here K1 A equilibrium minus K minus 1 A naught plus B naught minus A equilibrium. And then you subtract these two. Okay. If you subtract that, what you will get is minus dA minus A equilibrium by dt. That you will get is equal to, what will happen? You see, if I take this is constant. If you look at here, minus K minus 1 A naught plus B naught. Okay, so this you will get cancelled. What you are left with is K1 into A minus A equilibrium and K1 plus K minus 1 A minus A equilibrium. So that's what you will get. And since minus dA by dA equilibrium by dt is equal to 0, so this will be equal to minus dA by dt. Minus dA by dt. And why we are doing that? Now it is easy to integrate. This will give simply A minus A equilibrium is equal to A naught minus A equilibrium exponential minus K1 plus K minus 1 into T. So this is the whole equation, which generally we use to get the value of K1 and K minus 1. Is this okay? Is it clear?
Yes, sir.
Okay. So you can see here, if you subtract these two quantity, you will get K1 A minus A equilibrium. If you subtract this, then what you will get? K minus 1 minus K minus 1 your A minus A equilibrium. So basically you have to subtract these two. Idea is simply to express in this term, and it is quite easy. This is similar as dA by dt is equal to K1 into A. So it is quite easy to integrate, and from that you can get. So A minus A equilibrium will depend on K1 plus K minus 1. So one thing you must remember, that if you are dealing with A and B, in kinetics term, A concentration will depend on sum of these two rate constant. Sum of these rate constant. You see, this is sum of these rate constant. So A will decrease with rate constant A K1 plus K minus 1. So if I plot, if I take log and then we plot ln A minus A equilibrium versus T, then you will get a straight line. And the straight line, but rate constant will be equal to K1 plus K minus 1. So let us see how does it looks like when we plot A equilibrium versus T. Okay, so in that case, you will see that A decreases generally if A naught is greater than A equilibrium. So if A, you are dealing with this and both is present in the solution, then in one case A can increase or A can decrease. It will depend on if A naught is greater than A equilibrium, then it will decrease and go to it will decrease till A naught is till it reaches A equilibrium, and if A naught is less than A equilibrium, then it will increase. All right, and this is value is A equilibrium. This value is A equilibrium. Okay, and now from the equation you can see log A minus A equilibrium versus time will give slope. So if you get like this, then you are sure that A to B is a first order and B to A is also a first order reaction. Okay, so in reversible case also you can be able to know whether A to B is a first order or B to A is first order or not, just by plotting this A minus A equilibrium. Okay, so you have to measure concentration at different point, that will tell you A, and this value will let you know A equilibrium, or what you say A infinity. Okay, then slope will be equal to minus K1 plus K minus 1. So now you need to know the value of equilibrium constant to calculate both the value of K1 and K minus 1. We know that equilibrium constant is K1 by K minus 1. Here we can get from the slope what is the value of K1 plus K minus 1, that is K observed. And now since we have two unknowns and two equations, so I can extract K1 and K minus 1 value. Okay, K1. And do you know how to measure equilibrium constant? Yes? Anyone? I think I discussed in thermodynamic class or not? Okay, so equilibrium constant can be measured either by, there are two ways. One is direct way and another is indirect way. Okay, one is through measurement of delta H naught and delta S naught through calorimetry. You cannot know delta G naught, then you can know K. And the second way is to get the population at equilibrium. So if there is a way I can get what is the concentration of A and B at equilibrium, I can directly get what is the value of K. And that again can be measured through physical properties. Okay, through physical properties, where physical property is proportional to concentration. If suppose there is no other way to measuring concentration. So there are two methods to measure K. So once you know K and you know the slope of this equation, you can know what is the value of K1 and K minus 1. Okay, so let's discuss a bit complex reactions. How do we go about that? So here is A plus B giving you C, and this is a reversible reaction. And we assume that it is first order with respect to A and the first order with respect to B. So overall, it is second order in forward direction or first order in backward direction. Okay, in that case, what I will write, minus dA by dt will be K2 into A into B minus K minus 1 into C. All right, this is positive because in forward reaction, you have the A is consumed, and we are looking at the how A is getting consumed. So this will have positive sign, but since in reverse reaction A is getting formed, so there will be a negative sign, K minus 1 into C. And equilibrium constant will be given by C equilibrium by A equilibrium into B equilibrium. So equilibrium concentration of C divided by equilibrium concentration of A and divided by equilibrium concentration of B. Okay, in terms of rate constant, we can simply write K2 by K minus 1. Can we do solve this? It is difficult to do it because you will end up with a mess. So what is the different way? And there where your thinking comes into picture, the way you can do is again use flooding. If you remember flooding, okay. So what it is tells you that if suppose I flood the reaction with one of the reactant, B naught, B. So what does that mean? B naught is quite greater than A naught and C naught. In that case, K1 is K2 B naught, and which is basically K2 into B. Okay. So here what we are assuming that K1 is equal to K2 into B naught, which is equal to K2 into B. So now if you remember, we have this reaction. What is A? Let us see here. A plus B giving you C. All right. A plus B giving you C. So A plus B giving you C. So what we write, this is K2 and this is K minus 1. So what we have written, dA by dt is equal to K1 into A into B minus K minus 1 into C. Okay. And if I do it flooding with B, then I will write K1 into B naught, because this B will be equal to B naught. It is not changing much. So you can simply write K1 into A into B naught. Okay. And now K1 into B naught, okay, sorry, K2 here. So what I assume that K2 into B, K2 is a constant, B naught is a constant, and so we can write K2 into B naught is K1. And that's what it has been done here. So K1 minus K minus 1 into C. And now it is quite simple. We have already done that. How to solve this? All right. This we have already done in the first reversible reaction, A going to B. So here it is simply like A going to C. And based on that, we can calculate slope. And slope, if I plot again ln, your A minus A equilibrium versus T, I will get a straight line. The slope will be equal to, you see here, K1 plus K minus 1. Slope will be K1 plus K minus 1. And we know what was the K1? K1 is K2 into B naught. K2 into B naught plus K minus 1. And if I calculate K, that is equal to K2 by K minus 1. We know B naught, and so there are two unknowns and two equations. And so we can extract the value of K1 and K minus 1, or K2 and K minus 1. Is this okay? Any question here?
Sir, can you explain the graph again?
Okay, so let us see. Do you understand this graph? This one?
Yes, sir.
Okay, this is for A into B, all right? And this is your K1 and this is K minus 1. And then you will get A minus A equilibrium, slope minus K1, K minus 1. All right? Is this clear? Same thing
Yes,
we
sir.
are trying to do in this case. ln A minus A equilibrium versus T. This is ln A minus A equilibrium versus T. Same thing we will do here. A minus A equilibrium versus T. Because now you see here, it is similar equation. Minus dA by dt is K1A minus K minus 1C. So same thing you will get here. Only thing is now rate constant will be equal to K1 plus K minus 1. What is K1? K1 is K2 into B naught. If you look at the upper equation, what we assume that K2 into B naught is equal to K1. Alright, then I write K1 into A. So K1 is K2 into B naught. So what from the slope, what you get is K2 into B naught plus K minus 1. Remember, this is K2. This is not K1. This A plus B going to C. Rate constant for this reaction is K2. And C2A and B, this is K minus 1, reverse. So what we are going to get is not K2 plus K minus 1. What we are going to get is K1 plus K minus 1. Okay, K1 plus K minus 1. And K1, we know that K2 into B naught. So this is K2 B naught plus K minus 1. But I know the value of B naught, how much I have taken initially. And so still there are two unknowns only. Am I right? And if I measure the equilibrium constant for this reaction, I will get K2 by K minus 1. So K2 by K minus 1 I know. And I also know what is K2 into B naught plus K minus, which is equal to slope of this line. Once I know that, I can solve it to get the value of K minus 1 and K2. Is this clear?
Yes, sir.
Anyone, if you have any question, just let me know. So these are the three most important, elementary reactions. Anyone, if anyone has any questions, please let me know. No, just one minute. Okay, so any questions?
Sir, on the right side, minus j by dt, how you wrote K1A from K2A B naught?
I assume that you see K2 is constant, am I right?
Yes, sir.
Initial concentration is not going to change in the reaction, am I right? During the course of reaction. So this is also a constant.
Okay, sir. Got it.
A changes with time, not B naught. B naught is the initial concentration. It will not, B will change, but B naught is constant. So K2 into B naught is also a constant. I give that name K1. Okay.
Okay, sir.
So I will get from the slope K1 plus K minus 1. And what is K1 equal to? K2 into B naught. So K2 into B naught plus K minus 1, that's what I will get from the slope. And I know the equilibrium constant. And so I can know the value of K minus 1 and K2. Is this okay?
Sir, is it possible that due to flooding, the order of the reaction changes?
No, generally concentration based on order of reaction is certainly changing in the sense that now it is not second order, it is
Yes, sir.
0th order. So that is a different issue. Okay. So so that's why we are not writing B naught pe kya hoga. So it will not depend on B naught. That is the only thing which you have to keep in mind.
Okay.
Okay. So now you see here. Now it is a first order. Now it is no longer second order. जिसके साथ भी होता है, जिसको फ्लड करते हैं, उसके विथ रेस्पेक्ट इट इज a zero order. Is this okay?
Yes.
Okay, so now I will discuss differential equation. Okay. how to solve differential equation if suppose I cannot apply a steady state approximation. Okay, differential equation if I cannot apply, because already we have discussed all three cases. Only thing is that which is a bit complicated when if suppose I take this AIP, and this is the simplest one, but I will discuss more complex one. Is if both are suppose of the same order, K1, K2. In that case, certainly we cannot apply steady state approximation. And so what I need to do is I need to solve the differential equation, right? Differential equation. Now, what is the best way? Sometimes it is very difficult to solve a differential equation. Generally we do through computer, right? So we write computational programming or scientific, that is also known as scientific programming. Okay. Now question is, how I will differentiate in computer? Can I differentiate in computer using computer? Can you tell how to do that? You know, computer only knows plus, minus, multiplication and division. It cannot integrate as such. So if I want to integrate, what I need to do or differentiate?
You have to write a program.
Program. How do you write integrate? How will you do that?
So by using like equations like this, Picard's iteration, we use that for certain kind of. Basically, I don't know exactly. I don't remember exactly, but there are like in some steps we use iteration, and if we have x of I plus 1, like I is the step.
Yeah, iteration is generally done when you have to do several different, I mean, same calculation several different time. What I'm asking is, how will you integrate? Because computer only knows plus, minus, multiplication and division. Have you done computational programming before? Scientific programming, I mean. Okay, so let me ask another question. So suppose I have like second order equation. Okay, like alpha a square plus beta a plus c, or beta a plus some constant gamma is equal to 0. We can solve it. Am I right? How we can solve it?
So we will find the value of a using the formula minus beta plus minus under root of beta square minus 4 alpha gamma.
Great. So that way you can do it. Now I say alpha a3 plus beta a square plus gamma a plus delta is equal to 0. Can you solve it? Do you know any equation? Suppose I cannot factor it out. Can you solve it? Yes. Sorry. बंद हो गया क्या? Okay, let me open it. Can you solve it? Just let me know. I'm trying to open. Yes. Anyone?
So in J times we used to solve the um, this equation by the discriminant, but of particular form of a cubic x cube minus px plus q equals to 0, and it has a discriminant. And if the cubic equation is not in the form of x cube minus px plus q equals to 0, then we try to make it that way.
Hello, I will call. Just call me after 10 minutes. Okay. Yes. So, okay. Okay. So, I think now it is not. It has started working. So, insert. So have you seen van der Waal equation?
Yes, sir.
Yes.
Okay, and I think double A. Okay, so what is the order with respect to volume?
Three.
3. Okay, so it is 3 order. What is the equation? E plus
A plus A by square.
A by V square. V minus E is equal to RT for 1 mole. Am I right? And you can see this is third order. How I will solve for V? How many roots are possible? Tell me.
3 roots.
3 roots. Good. 3 roots because this is third order. Now how to solve this? Did you try to solve any time? No. Okay, so let me tell you what we generally do. We use scientific programming. And for scientific programming, what is basically needed is you should know what is known as, this is mathematics certainly, numerical analysis. Have you heard about this? आपने सुना है इसको, numerical analysis? This is one of the topics in mathematics, and that is very important if you are dealing with scientific programming. So you must know. If you are interested, you can start studying a bit. Scientific programming. This is basis of scientific programming. Everything is done in terms of plus, minus, multiplication and division. Even solving a root. Have you heard about Newton's-Raphson method? No, probably not. You will study that. That is one of the way to solve if the
We
root
have
is.
heard, but it is not taught explicitly. We have heard somewhere in the other course.
Okay. So this is Newton-Raphson method is one of the way in which even if order is 4, 5, you can solve it. Okay. And you only need to do plus, minus, multiplication and division. Okay, plus, minus, multiplication and division. That is what is going to be used when you are trying to solve, for example, van der Waals equation through Newton-Raphson method. Okay. And similarly, we have for differential equation, solving differential equation, we have what is called, this is one of the method. RK method. Okay. So these are the methods which are very important. So numerical analysis, if you want to do scientific programming, you need to learn, numerical analysis. And once you know the numerical analysis, now it is simple coding the way you do for any other programming. Please remember, I am talking about scientific program. It is not simply like, So for example, if I want to solve equations, root of equations, I want to fit a curve, fitting can also be done. And there are different ways of fitting. Sometimes you may require differential or integration. Solving a differential equation, one of the method I am talking about this. I will a bit discuss in the next class what is this method. But please keep into mind that if you want to do, only thing here requires is you require several iteration. Right? You will start with some guess, what is known as wise guess. There is a way of doing that also. And from there, several iteration it will do till it will find out, the the root of equation. Okay, right root of equation, right solution for example, in this case, volume. It will go on doing iteration. There will be some condition put so that it will stop there. After a certain, when it satisfies a certain condition, it will stop there, and that equation will be the right, right value of the root. Same about integration, and you can see that when I will discuss in next class, you'll see that I am only going to use plus, minus, multiplication and division. I am not going to use any other thing. Means I am not going to, the way we do integration or the way we solve the differential equation, I am not going to do like that. But if number of iteration is good enough, if we put right condition, we can get almost exact value of the solution. Okay. Any other questions? Otherwise, I will stop now.
Sir?
Yes, please go ahead.
So which text do you refer for this lecture today?
This any if you go to any like Atkins, if you go, or any physical.
Well, would Ladler suffice?
Ladler, I believe that yes, Ladler will also discuss about that. It may not be everything. Means like any book you will go, everything you will not get, but most of the thing you will be able to get. For example, the complex this reversible reaction, which I told that you need to do flooding, and to get the solution for K2 and K-1, that you will not get in either Atkins book or any other book. Okay, but other things you will be able to get. For example, reversible reaction in any book, Alberti, Atkins, Ladler, any book you will be able to get. Okay, so all three elementary reactions which I discussed, all you will be able to get in any of the physical chemistry book which is of graduation level. Okay. Some of them may have discussed RK method also, some may not have discussed. So yes, but you need to know, at least if you are interested in doing, being a chemical engineer, that is certainly required whenever you are thinking of writing a scientific program. So please start studying, numerical analysis a bit. Okay, I start writing few of the programs, and you will love it. For example, van der Waal equation, you solve it. Okay. Anything else? No? Okay, so then I will stop here.